this is my talk, writing a Wordle solver in Scala. It was actually going to, briefly, it was going to be writing a Wordle solving tweet bot in Scala, but I didn't get to the tweeting part. So it is writing a Wordle solver in Scala. We all love Wordles, right? But the Wordle solver that I'm going to show you, they're not like the way humans solve Wordles. It's not like, oh, there's an I and a G, and we must have an N between them for an ing sound. It's not a linguistic theory. I haven't written the Wordle solver like that. The approach I've taken is that it should try to find the best choice from all available words, even the really quite unusual, obscure words that a human wouldn't think of using, because sometimes they can get better results. So if you're going to write a Wordle solver, there are 3 questions you want to answer if you're going to write a Wordle solver. They get increasingly harder as you go along. So the first question is, what words are possible? What words are possible correct answers given the feedback our guesses have gotten so far? So that's the first and sort of easiest question to address. Then there's what's a good choice of guess for our next move? So that might be doing a small bit of look ahead to think about okay, what's the consequences of making our guess? And then finally, the hardest question is, what's the best possible guess you could conceivably make in this situation? For the start word and then for your subsequent words, what's the best play? Now, we're probably going to run out of time before I fully cover this final one, but in the Q&A, you're welcome to ask me more about it. Okay, so next slide. What words are possible? Okay, so there are actually about 2,300 common words that can be the answer in a Wordle, and an additional 10,000 or so uncommon words that you're allowed to type in. So the first step is to get hold of that list of words. They're in the JavaScript source code, so they're not hard to find. So if we go to Wordle and we inspect the source, we have a look in here, and we just search for a word we know is in there, perky was an answer a little while ago. So here we can see these are all the words in the source. They're in the order that they're going to happen. And so all 2,300 words are there in an array, followed by the additional 10,000 uncommon words in a separate array. So I've copied and pasted this out, and I've stuck it into a sort of sorted file, just so that I don't have to spoil Wordle for myself. So they're in alphabetical order, and I don't know what's going to happen the next day, so that's good. I've put a star against the ones that are the common words, the ones that can actually be the answer. Wow, cavil is considered a common word. I didn't know that. But then the other ones, these ones are so obscure that they will never be the Wordle answer. So, see now. So for our first move, we know that there's going to be 2,300 possible words. But as soon as we enter a guess, we get feedback that helps us to narrow down that set of possible words. So supposing I were to do this, that's my first guess, and I hit this, and we get feedback. So every letter is correct, or incorrect, or misplaced. So that's 3, each letter can have 3 different values of feedback. So 3 fixed values, that sounds a bit like a Scala enum value, a Scala 3 enum, so yay! So we can implement that as a Scala 3 enum. So if we have a look in here, oops, so if I look, here we go, there's a Scala 3 enum. It's got incorrect, misplaced, and correct. So misplaced, that's the yellow one. Incorrect, which is white, and correct as green. So that is a nice clean representation of just a single letter's feedback, but the information we get after a guess is for all 5 letters. So it makes sense to have a representation that holds all 5 letter feedbacks at once. So I've called that a word feedback. So here are the tests for word feedback. Here we go. So you can see that a word feedback takes in 5 values and represents them together. Now, you can see that it's most of the time in the test, it's actually kind of more concise just to use the emoji representation. So this could be a bit tricky for people with red-green color blindness, but for me, it's been quite handy. It's quite a nice, concise way of representing the feedback in tests. Okay, so now to work out which of the 2,300 words are still possible correct answers after getting this feedback for our first guess, we need to see which of those 2,300 words, those possible 2,300 words, would give us that feedback for our guess of a side if they actually were the target word. So so what we want is a method that can reproduce Wordle's logic for giving feedback on a word. So we want a method like this. It's it takes in like a candidate, a guess that we might type in, and it tests it against like a potential actual word, the solution to the Wordle, and it tells us what feedback we would get if we were to do this combination of things. I'll note that I'm using word here as a type alias for string. So these are just strings with a slightly more appropriate name. Now, so when we use this method, it would work like this. Okay, so this is what it would do. It would say, okay, our guess is sassy, but the right answer is grass. So the feedback should be this. So that's what we want to implement. The fiddly part here is making sure that we don't mark too many letters as misplaced. There are only 2 S's in grass, so we shouldn't give feedback that implies there are 3 S's. That's why the third letter feedback here is blank, not yellow. So it's an S, but it's blank. What Wordle does is give feedback where the leftmost copy of the letter wins. So that's this one here, the S there. So we have to reproduce that. We have to match that behavior. So going into IntelliJ, well, okay, so here is the implementation of that feedback for method. Now, I don't know, I maybe have a bit of a blank spot on this. This is like the clearest kind of implementation I could come up with. It's still not that clear. So afterwards, if people can tell me like a clear, simple way that's still like intuitively correct to work this out, I'd be very happy to see it. Just to describe this very quickly, we take the word indices, that's the numbers 0, 1, 2, 3, 4, so the 5 possible indexes of a letter in a Wordle word, and we partition them into words that have a correct match in the candidate and those that don't. So those are the correct ones, and those are the ones that are not correct. And then for all the ones that weren't correct, we work out, well, okay, from the actual word, how many of those letters in the actual word are there, how many A's and R's and S's there are, and then we fold left, we sort of iterate left over our candidate word, saying, well, okay, are you trying to use one of the available letters? And if you are, we'll note it down as a misplaced letter, and we'll decrement the list of available letters still left. So it's all a bit tortured, but eventually at the end of it, we can say, okay, this is the word feedback for this and this. And if someone wants to come up with a nicer implementation, yes, please do. Okay, let's just check that it actually does work. So here's a test. Right, so this is implementing what we saw before. For the word sassy, and where the actual answer is grass, we should get this. So let's just run the tests. Okay. So, yeah, we can see that test passed. It did output the correct output, so it works. Okay, so that's great. We've got a feedback for function. Let's go back to the slides. So we can now write code like this, where we say, okay, so given like a list of possible words, we can filter them down with a new piece of evidence. We can say, now what are the possible words now, given that we've seen this feedback? So we say, okay, for each possible actual answer, would doing the guess that we made get the feedback that we actually got? Okay, if it did, then cool, this word is still possible. Now, this thing of like first guess the first guess word, and the feedback for first guess is quite often needed together in this code. So I'll put them in a dedicated case class called evidence. So evidence is a guess plus the feedback for that guess. Okay, so that's quite, they go quite nicely together. And also because evidence knows what the word is, it can display some slightly better feedback to me as a developer than word feedback did. So word feedback could do the blank emoji squares you see people sharing on social media, but evidence now knows the word that the feedback is for, so it can do a nice display of the feedback like this. Let's just run that. So there you are. It's sassy. This is using Howie's fancy library, by the way, for coloring the letters, but it looks very nice and pretty. So I found that really helpful while I was working along and trying to work out what's going on. We can also go slightly wild with Scala 3 extension methods. I mean, they are the spiritual successor of implicits, so why not go wild with them? I'm going to put an extension method onto string or like onto word so that we can write some code that reads more nicely. So let's have a look at that extension method. Here we go. Okay, so we're extending word, which is just another word for string. And we're going to say, does this word comply with its evidence? It returns a Boolean. Does it comply with the evidence we've seen? Okay, and it asks the question pretty much the same as before. It's like, okay, well, for this evidence's guess, would this word produce this feedback? And if it does, then this word complies with its evidence. So that lets us write nicer code like this. So rather than having to write words, blah, 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 we can just say words filter for those that comply with the evidence. Words filter complies with evidence. Okay, cool. All right, so this is like this borderline readable code now. That's great. So we now have just enough code to make a first rudimentary Wordle player. Let's just define a pair of Scala traits to define what we mean by a Wordle player. What does the Wordle player have to do to be a Wordle player? Okay, so a Wordle player is just a chunk of code that maintains some state as it plays a Wordle game. The player state is capable of saying what move it wants to make at the current point, and it's capable of generating an updated state given some evidence that comes in. That's the guess and the feedback that comes back to get some updated state. It's quite a simple interface. Unlike a human player, it doesn't get a nice board to look at to tell it what's happened so far. So it has to maintain its own record of incoming evidence if it wants to do that. But actually, that doesn't seem to be much of a problem in the implementations I've done so far. Okay, so let's look at our very first Wordle player. Okay. Right, so it's really quite a simple Wordle player. It starts off with, okay, here are the big old list of common words. So to start with, those 2,300 words are all the possible words that could be. So there's starting. And it will make, in its considered opinion, it will always guess the very first of the possible words. So it just picks the first one that from the words that it knows are possible. And then when the evidence comes back, like for the guess and the feedback, it just filters its available words to the ones that comply with the evidence. Okay, so it's a very simple Wordle player. How well can it possibly do? Well, let's have a look at some tests. Okay, so we've got this this player. And shake was a word that came up recently in Wordle. So let's see how it does with that. Let's run these tests. So, okay, it actually did manage to do the Wordle. I mean, it wasn't the fastest, right? Most people probably, this is like a bad day for them. This is like a bad wake up. It went aback, Drake, flake, quake, and shake, but it did get there within the 6 guesses that it's supposed to. Oh, and I should probably mention that what I've done here is I've introduced a little game class here. So the game class has the job of knowing what the actual target word is, that's the shake it, and asking the player what move it wants to make, and then passing it the evidence once the player makes that guess. And it also checks that the player isn't trying to do any illegal moves or go beyond 6 guesses or anything like that. Okay, so, well, this player did really quite well. Well, did it sort of right for the first one. Then, like, for Kulk, which was another word recently, look at this. It gets it in 2. I mean, and I didn't even try that many different words. It's just got there quite quickly. That's almost humiliatingly fast. Or you could just say lucky, possibly. But, okay, so it did well there. But it is not the world's greatest player, so it does fail sometimes. Sometimes it takes more than 6 guesses. So I wrote a little bit of code here to say, okay, for all of the common words, the 2300s, of all of these 2300 words, are there any where it's not successful? And yes, indeed, it is not successful sometimes. There's 58 words where it couldn't do it. So for instance, for this word here, bunny, this is what it did. It went aback, beefy, biddy, bobby, buggy, bully, but it never got to bunny. So you know, sad ending to that story. I mean, but you know, it works. It fails for about 60 out of the 2300 words, but it's kind of better than I thought it would be. Okay, so we managed to answer the first question. What words are possible? We've done that. We've got like a gold star of some kind, or a green square. But the next choice then is, what's a good choice of guess? Well, supposing we are playing a Wordle game and we've guessed grain on our first move, right? And we got this feedback. What is a good next guess? What's a good next guess for the Wordle player to make? Well, thanks to the code we've already written, we can find out what words are still possible for being the correct target word. I think I actually have a test for that somewhere. Let's just see if I can find it. Okay, yeah, so here's a test that says, like, okay, given grain gets this, then what are the possible words after the first guess? So let's just run that. Okay, and we can see it says there are 34 possible target words after grain. Okay, great. So there's 34 possible words it could be. Rack, track from all of these ones. In fact, sorry, yeah, there is a bit more code here for, there are 34 possible words it could be. Now, the thing you've got to get a handle on here is that all of these words are possible, and that all of them are as likely as the other. You might think that, like, I don't know, rack is a slightly rarer word than erase or something, but they're all considered possible words and they've all matched the evidence. They're all equally likely. So fact is, we've got to face it, we probably aren't going to guess the right word with our next guess. I mean, like, it's like a 1 in 34 chance of guessing the right word. No matter how clever you are, there's a 1 in 34 chance of guessing the right word because this is all the information you have. The best we can hope for is choosing a word that is good, that would narrow down, that would get feedback that would narrow down our word set list. So from going from 34 words to like a much smaller number of words, that would be really good. Okay. Of all of the, like, it doesn't have to be one of these words. We could choose like another one of the 1200, but let's just for an example say, okay, let's try draft. Okay, so I've written a bit of code, a bit more code here to say, okay, what's going to happen if we guess draft? Okay, so we've got our second guess is draft, and what we're going to do is we're going to group up all of the 34 words by the feedback they would get for for draft. So the feedback that draft would get for that possible word. So the 34 possible words, for each one of those possible actual correct things, you say draft, what feedback would you get? So that's what this map is here. So you guess draft, and you would get this set of words for this given feedback. So let's just run that and see what it looks like. Okay, so turns out there are 9 different possible feedbacks we could get for guessing draft. After this has happened, we guess draft, and we've got 34 words. These are the 9 different possible feedbacks we could get. Okay, so let's just have a look at that here. So we got draft. We guessed draft. So this is how it breaks down. This is the possible consequences, the possible feedback we could get for the word draft. So, for instance, if the real correct word was Drake, then we would get 3 greens at the start. So, like Drake, drama, drape, and drawl, they would all get 3 greens. It would all give 3 greens to draft. Whereas craft would give 4 greens to draft, which is very generous and nice. So that is good, but you'll notice that there's a big old group up here. Like there are 17 words that would give just 2 greens to draft. So brace and break. So the chances here are not great. Like if you think about it, because each one of these words is equally likely, there's 17 chances out of 34 that we are going to get one of these is the actual correct answer, which means we have like a 50% chance of getting this and ending up in a word set of size 17, which is, that's a pretty big group size. So we can actually work out what the average expected size of the group is, based on the sort of weighted probability of this happening. So this works out that the average number of possible words after you guess draft is going to be about 10.6, about 11 words, which is, like, okay, so you've narrowed it down from 34 words to about 10, but is that good? Is that great? Well, it turns out that there are better words. For instance, there is the word Celts. So we can see through some analysis, I'll just pull this onto my screen, that Celts does a lot better than draft. So here's draft with this little breakdown, and here's what Celts does. So you can see that there's a lot more different possible feedback outputs. And because there's a lot more, the groups that you generate tend to be smaller, and it's also kind of a bit more even as well. So, like, there is one group that's bigger than the others, but it's only 5 big. And what this means is, for the word Celts, the average expected word set size is just about 2 words rather than 10. So Celts is way, way better. Now, what this means is that what we're trying to do here is reduce the average expected word set size. So we're trying to choose a guess that gives us the lowest possible expected word set size. So let's have a look at the player for doing that. One step. So this is a player that does 1 step ahead evaluation. So, okay. So this feedback table here is an optimization. What's happened here is that in advance, this has worked out every single combination of possible word and target word and calculated the feedback. So you didn't have to run that slow code I showed you before. And it's just stored it as a result in an array. And as it happens, because word feedback can only take one of 3 to the power of 5 different values, which is 243 different values, it fits in a byte. So if we have a look at word feedback, word feedback. Where is it? Somewhere around here. So word feedback is represented as an any-val, but actually, for the purpose of the JVM, it's represented by a single byte, which means it takes up a lot less memory. So going back to that one-step player, what do they do? Well, they have a set of the initial set of candidate words, and this set is representing not just the possible words that could be, but also the sort of 10,000 words that you're also allowed to play. And when it comes to decide its move, it iterates over every single one of those candidates, and it has a look to see which one is going to minimize the expected average resulting size of the possible word set. Let's have a quick look in there. So what it's actually sorting by is this thing, the evenness score. So it turns out that if you go over the possible sets and sum the squares of their size, sum them up, then what you get is a value which is lower the more even the word set distribution is, and it basically corresponds to lowering the size, the probable resulting size of the word set. So, oops. Okay, so we can see here that it's to select basically of all of these ones here, of all of these candidate outlooks, it selects the earliest one, the one with the lowest score, and it says that's going to be my guess. And whenever an update comes in, it uses this optimized feedback table to say, okay, well, of all the candidates I've got, I just want them to comply with this evidence, just like before. I think I'm probably running a little low on time, but I will show you this one running. Let's have a look at this. Okay. Okay. All right. So here's the one-step player. Here's it playing with a word in the fullest of common words, and we'll see it printing out like its match. And then after that, we're going to do something that kind of moves on to the next step. Let me just run this bit first. Run it. Okay. Now, there we go. Okay, so you might have spotted this being talked about on the internet, possibly if you're into Wordles, you might have seen some people saying, oh yeah, this is the best starter word. So it turns out that if you want to score by evenness of the resulting candidate set, that row 8 is the one that gives you the smoothest distribution for the first word. So here it was trying to get the word a back, and it guessed first with row 8, then slick, then a null, and a back. So it got there in 4, which is not too bad. I'll just show you what the distribution of the word set for row 8 looks like. So there we go. So you can see that there are still, like, if you guess row 8 on your first move, you're most likely to get no answers back at all, but it's otherwise relatively even. I think we can compare this to, so there's other words like trace. So trace actually gives more different values. It gives like 150 different possible feedbacks, but the distribution isn't quite as even as row 8. So row 8 actually ends up being slightly better. I think my time is up. I'm very sorry about that. I've not managed to go as fast as I could. Oh yeah, I would love to tell you about the sad loss of Agora, because Agora can facilitate faster solutions in particular situations, but the New York Times has just banned the word Agora. It's got rid of offensive words, which I think is fine, but also obscure words like Agora from the common list of solutions. And you're no longer allowed to play Agora, which I think is unfortunate. But anyway, we've managed to do this. We managed to find what was possible, what's a good choice of word, and then the final question is, what's the best possible word? Now, I would love to take you through my code for doing that, but I don't really have time. I will just try to point you at, give me a sec, try to point you at this page here. Now, I've got implementations of the strategy on this page here. This guy here, Alex Selby, is fascinating. He's produced a beautiful description of the algorithm, which I'd love to take you through. It's really, really nice. This is some stuff called minimax in computer science theory. And I'll also tell you that Alex Selby once won £1 million by solving a puzzle that the creator had said could never be solved, and he did it in about 3 months.